No, we don't have to do the standing up if you don't want to, but if you want, stand up when you clap, that's okay. But I would like to introduce our first two speakers. And the first one is David Edsbäcker from Kraftringen, Project Manager of Business Development. You can come up. We can clap at least. And Jonatan Kusse, he's an energy engineer from Energy Opticon. And they will speak about how smart optimization can lower the temperature in existing grids.
Yeah, that is correct. So my name is David Edsbäcker and I work in Kraftringen. And I'm the project manager for Smart City Accelerator that Henrik mentioned before today.
Yes, and I'm Jonatan Kusse, and as Moa said, I'm an energy engineer at Energy Opticon, and I'm also been part of developing this product that we're going to show, the so-called Smart Optima Heat Network for forward temperature optimization.
So what we will go through today, you can see in the title here, securing a lower grid temperature through increased digitalization using heat load forecasting and feedback from the grid. And that might sound quite complex and long title, but what we really are here to talk about is how we optimize the existing grid. And we showed in the project by quite small means we can actually optimize the forward temperature just by using new technology. And in this case, we used Energy Opticon for that. And I need to change my slide. So a brief outline for today. First, I will give you a general background about the project and also some general information about Kraftringen's district heating grid. And after that, we will go into the core of the presentation, which is how we choose to work with more digitalization to optimize the forward temperature. And then I will wrap it up with a conclusion. But the key message I would like you all to take home today is that you shouldn't forget about the existing third generation grids. There are much things that could be done by just having a smarter control. So I believe we should do this in parallel to building new fourth generation grids. We should also look at the existing grids. So Smart City Accelerator, or SCA, is an Interreg finance project for Öresund, Skagerrak, Kattegat region. And the duration is from 2016 to February 2020. And the overall budget is 6.5 million. And the main theme of the whole project is optimizing energy systems, reducing the dependency of fossil fuels. So there's many different angles of this project, and Kraftringen has been involved in one of those 6 themes. So we choose only to look at how we can optimize our existing grid. So you might remember this slide from Sara's presentation before, but I will give a quick recap. So Kraftringen's grid mainly consists of third generation. We have a large and quite complex grid. It goes all the way from Lund up to Landskrona, where we're connecting to another neighboring city. And we produce annually about 1,000 gigawatt hour of heat per year. Half of that heat is supplied by our largest production plant. It's a combined heat and power plant called Örtofta. And in that plant, we also produce about 150 gigawatt hours of electricity per year. And since we have a quite complex grid, we do also, of course, have heat losses. We account the heat losses to be about 8 to 15%, which is normal for the size of our grid. So previously, we control our forward temperature by a quite static outdoor compensated curve. So you can see when the outdoor temperature are higher than 8 degrees, we supply about 78 degrees in forward temperature. Then when the outdoor temperature drops below 8 degrees to minus 8 degrees, is a linear increase of the supply temperature. So when it's really cold outside, colder than -8, we supply about 107 degrees. So we tend to have quite large safety margins in our grid. We supply a bit higher temperature than actually necessary because we don't want complaining customers, so that's why. And also previously we didn't have any feedback from our grid, which has changed. Nowadays we do have, which Jonatan will talk about later. And if we look at the actual outcome during last year, which is the yellow dots here, you can see that we actually follow the curve quite well when it's cold outside. But summertime we tend to go a bit higher in the heat. But in summertime we have quite much excess heat from the neighboring grids, and also we do have observation chillers in our grid. And those chillers demand a certain temperature, therefore we cannot go too low in the summer. But the most economic and environmental potential will be if we decrease it during winter time. That's where we really have much to save. So this is really the same slide as you saw before, but now it's presented in a slightly different way. So you can see the black curve here. That's the actual forward temperature that we supply in the grid. And you can see the axis to the left-hand side, which is the supply temperature. On the right-hand side, you have the load forecast. That is a gray background in the figure. And the red dotted line here, that's the temperature curve. So you can see we follow the curve quite well in wintertime, but not in the summertime. But I will come back to this slide later with the actual outcome of how we do it today, and you might see a difference here. So why do we want a lower temperature in the grid? Hopefully you all know this by now. Since the morning they cover quite many of these aspects. First of all, if we go low in the temperature, we do have less heat losses in our grid, which is of course what we want. And also if we go low in the temperature, the efficiency in the steam and flue gas condenser will also increase. Therefore, we can produce more electricity for the same amount of fuel. And also if we go lower in the temperature, then we can use more excess heat from neighboring industries and different stakeholders. And we don't need to boost that temperature up as much as we do today. And lastly, there's large economic and environmental gains. We calculated the savings of about 100,000 euros per degree we reduce the forward temperature. But there are some challenges. We cannot just reduce the temperature without any control. Then the customers will be calling us and being very mad. So we need to take this into account, the challenges we do have. And one of the big challenges is the performance in the substations. Kerstin mentioned it this morning that there's a problem with malfunctioning substations throughout Sweden. So the annual average supply in Sweden is 86. But if all the substations in Sweden was working perfectly, it would be enough with 70 degrees forward temperature. So that shows that many district heating companies, just like Kraftingen, has a problem with malfunctioning substations. And the problem is we do not own these substations. So there's not that much we can do about these malfunctioning substations. We do have price models that encourage a low return temperature and especially a flow tariff on our larger customers. But that might not be enough. And also in our grid we have a time delay. That is the time it takes for the heat from Ärtofta, our production plant, to reach the most further outer part of our grid. And for our grid that takes about 6 hours. So during that time, of course, we lose heat, we lose energy. So therefore we normally refer the most outer part of our grid as critical. Because in these points we normally have more problem of keeping up the correct heat amount, the correct temperature. And also we do have some supply thresholds in our grids. And we also need to take into account disturbances such as weather, like a sudden weather change. We need to have some buffer in our system that takes this into account. But now Jonatan will talk about how this new program can be used to solve many of these challenges we have.
Yes, so now onwards to the solutions. And as you see here on the board, we're going to talk about forward temperature optimization. But if we're going to do this in a proper way, the thing we actually need to talk about is the full energy system optimization. So traditionally, an energy system for district heating has been viewed as 3 separated parts, where you have production, distribution, and the end customers or the consumption. And this, of course, will lead to a big risk of sub-optimizing each system independently. So what we want to do here is, of course, merge all of them and look at a system as one. And what we do here now is a start to that, and merging the production with the distribution. And that is what we do with our product, Smart Optima Heat Network. So what we need to consider then for what's new that comes with the distribution. So as David mentioned, we do have time delays, but this is not only a problem, this is also a potential where you can, you need heat at a certain time at the end points of the network. You just have to time it correctly when you increase. And so we need to model the network reaction of an increase or a decrease in forward temperature. We have the supply thresholds in the same way. You could have a pump or that is small, or you can have a pipe that is too narrow. That means your flow is limited. Sometimes you would maybe need higher temperatures for pushing enough power to this area. But then when optimizing the forward temperature, you can instead just raise it when you really need to, but other times of day keep it low, instead of this safe way of operating and always keeping it up. We also have to look at some model constraints, such as temperature limits. We know there is an upper and a lower limit mentioned in the presentations this morning for various reasons, technical reasons, legislative reasons, design criteria. And then when starting to implement, we would also like to work with kind of an easy, like a safe approach of implementing. So we do not everything at once. We try out optimizing a little bit, letting it go a little bit lower, and then if that works, we can keep on increasing. Feedback from the grid, David mentioned before, and that is important to take both the current status, so we know, okay, where are we now? Do we have a network that is hotter than usual, or is it colder than usual? And that will then help us take the decisions for the future. What should we do from now on? Then these measurements, of course, will also be used to improve on the model, to adjust the model parameters to better represent reality. And the final point here, which we shouldn't miss out on, is the weather forecast, which in a sense is the base of everything, both forward temperature and the load forecasting. But say we now do all of this, what do we have to gain? So we do get overall a reduced grid temperature, and this is a lot due to what I talked about. If you need high temperature for certain reasons, do it with the right timing, do it for the right period, but don't do it all the time. So overall, we will see a decrease. We will also have the chance of improving on production planning. Using the forward temperature is something that can be done and has been done in control rooms, but usually it's on a personal know-how basis. So this tool will give the option of having a common ground and a tool to rely on when you're unsure. We also can see here that we will improve on the grid knowledge. You can use this tool to analyze. Say I have a critical point that means I have to go out with a certain forward temperature. What if I were to improve on that one? Swap out the heat exchanger. How much could I earn? And the last point, of course, we are talking about a tool for economical optimization. So this means you will get an economically optimal production plan. And when adding the forward temperature into these calculations, of course, it's going to be more optimal than when you don't. Yeah.
Thank you. Very good. So here you see the same slide as before. But if you have an eye for detail, you might notice that something changed here. And that's around here. So we installed the program in the beginning of March this year. And we can see now actually the actual forward temperature is lower than the initial curve. And you might also notice that the curve, the forward temperature now in the grid, that is the black line, is more even than before. So we don't need to go as much up and down in heat because the program actually knows how much heat that is stored in the grid. Okay, so this is the same as before, but with actual outcome this year. So you can see the blue line is this year, the yellow line is last year, or without the program. So we actually decreased the average temperature with about 2 degrees in our grid. But we need more periods for evaluation during next heating season as well. And this is the forward temperature from our largest production site, Örtofta, which before was quite constant, 100 degrees. But now with the program, it suggests to go lower in temperature when it's optimal to do so. So in average, we also here reduced it with about 2.5 degrees.
Yes, and this is about economical optimization, but I guess you can come and ask me. So I'll just take the result that we earned about 21,000 euros in the 2 months we tested this. Yes.
So some fast conclusions here.
Yeah.
Well, digitalization causes more increased grid knowledge. By taking more parameters into control, we can actually lower the grid temperatures and reduce the safety margins. And also we can do proactive instead of reactive measures. Now we can react and reduce the temperature without having customers calling and complaining about that it's too low, because we know it in beforehand. And also lastly, there are many and large economic and environmental savings by doing so. And the future scenario here, we think that now the system boundary is our grid. We want to expand our system boundary and also include the end user. So by having the end user, taking that into account, we can do peak shaving in the grid, which then will cause even further flexibility for us. That is everything we had. Thank you very much.
Okay, thank you very much. Bravo. All right. So do we have any questions for the speakers?
Yeah, I was thinking about, you mentioned you have absorption chillers.
Yeah.
Those will work worse if you lower the temperature. Do you have a plan for changing that production of cold or cooling?
Not at the moment, because it's mainly in the summer we have that problem. Otherwise, we go high enough in the temperature. And in the summer, we have so much waste heat from like the industries nearby, so we don't have any problem in the summer really with the heat demand. So for us, it's not that large of a gain to energy optimize summer months. Of course, we still want to do it, but it's not critical. Yeah.
All right, we actually have to move on with the program, but I wanted to ask a quick question. How much more are you expecting to be lowering the temperature in the grid? Because you already said like about 2.5, which is a lot of money. You said 100,000 per degree, right?
Yeah, so now we evaluated during 2 months. Of course, we need to do a longer evaluation, and we believe the more points we take into account, if we have more measurements out in the grid, we can fine-tune. This is your...
No, but I would agree. You're definitely onto the right thing. That means we can run, if we have more in the grid, we can run closer on the margins, and that means, be more brave about how much can we actually reduce and when. So, this pilot has been with a restrictive setting, so definitely more, I would say.
All right, wonderful. Thank you so much. You can... wait.